Simon and Ron, to my Science Mysteries Laboratory. All right. So Simon, do you remember kind of what we talked about last time? So
Yes.
we had talked a little bit about, what gravity is and what makes things drop to the ground like that. We talked a little bit about the electric forces and a bit about how magnets work. So I was wondering, do you guys have any questions about that? Do you think that that was interesting or plausible or implausible? What do you think?
I don't know what plausible and implausible
Oh,
means.
that means whether it's true or whether it's
Or
false.
believable.
Right?
Plausible means
It's like,
believable.
I told you that gravity was just the electrostatic force, is what I attacked. So, what do you think? Is that true or is that false? Did I just make that up?
I've never heard it
I
anywhere
think
else.
it's true.
You think it may be true? Okay, all right. I've got at least one believer. Okay. But today, what we're going to be doing is we're actually going to look into light. You see, we have light here. Okay. Here we go. So we'll start out with this thing here. So let's see what happens. So do you think anything weird is going to happen if you shine light onto that thing? Because you can't touch it, right? It's why don't you go ahead and try? Go ahead and shine the light on that. Shine the light on that and see what it does. Let's see what it does. Yeah, it seems to be. It spins. It causes it to spin. So turn off the light. Let's see if it stops. So you press the top there. Let's get it to slow down for a second here. Get it to stop.
It's slowing.
Okay, so it's
Yeah.
kind of stopped. So let's turn the light back on and see whether that really caused it to happen. Yeah, see if you can get it closer. Yeah, there it goes.
There it goes.
Yeah, see, you're not touching it. It's not being blown from
Pushes
any
on the
wind on
black.
the outside.
Pushes on the black
But
side.
yeah, it's kind of weird. Looks
How
like,
could light do that?
well, based on which way he's pointing. I mean, could you think you could get it to spin the other direction? Maybe if you point it
No,
the other way.
I don't think so.
First, you gotta get to slow down, but maybe not.
True.
But that's kind of weird, isn't it? That
Yeah.
just light itself can cause that thing to turn around.
But it can't push it. And after all, it's in that light bulb thing.
That's right.
Yeah.
It's completely sealed off from the outside world.
The only light gets in there.
So, but that kind of shows that light can has some energy. It can do some work. So there's like the energy was in the battery, and then it came out as light, and then it started turning these veins around.
Yeah.
So that's one interesting thing about light, that it can do stuff. And
Yeah.
I have perhaps if you have a solar panel, you can turn light into like electricity directly. So I have a big solar panel outside there. And so light, that's one of the things about light.
Yeah.
It has energy.
You know about solar panels?
Yeah.
Yeah, it makes electricity. Yeah.
But somehow, there's this whole question here. What is light? And believe it or not, people still don't quite know what light is and exactly how it works. It's like if I got my flashlight here, and I turn it on, then something is coming from the light bulb in here going out that way, right? Through seemingly nothing, right? This works in the vacuum of space as well, because we can see the stars, and those are coming through to us from millions of light years somehow, right? So some people think that, light is a wave, which is like a sound wave, which is basically when you have some particles like air, like I'm talking to you, So you can hear me, right? So I'm sitting over here and you're over there, but yet you can hear what I am saying. And that's because there are sound waves. There's like, I'm creating a compression, and that compression is eventually hitting your ear.
That travels
Now that's
through-
one way that
travels through the
that's
air.
one way that light could travel. It could travel like sound. But the other way light could possibly travel is if it were some kind of bullet, right? So let's say that this is light, and I could throw it towards you, and then eventually it hits you, and that would be like light as being some kind of particle. That means that my flashlight here is actually spitting something out at you, right? You know, maybe that might explain how this thing worked, is because maybe it's spitting out bullets, and the bullets are hitting the veins, and it's turning the veins.
They go through the glass.
Yeah, and then they go through the glass, because the glass is transparent, so it doesn't stop the light bullets,
Yeah.
right? But, so whoever figures that one out gets Nobel Prize, okay? Light. Well, and then you'll hear confusing things like, you know, light is a wave, it's also a particle. It depends on which way you look at it. I mean, does that make any sense? Does it make any sense
Like,
that something
Particle.
changes?
What?
Something changes its characteristic completely, depending on whether you're looking at it in a certain way. It's like, have you heard the thing that if a tree falls in the forest and if there's no one there to hear it, does it make a sound?
Well, the
What do you
energy goes, the sound energy goes out, so.
I would think it makes a sound,
Yeah,
right? It
it
doesn't
does.
matter whether anyone's looking at it or
Yeah.
not. It's going to do the same thing. But seriously, physicists think that no, the tree did not make a sound because we were not looking at it. It would be literally that kind of interpretation you would have to accept. And this is one of the reasons why light is so confusing, because, you know, physicists say stuff like that, you know,
Mhm.
it's a light when you do one experiment, it's a wave when you do another experiment. It's all terribly confusing. Me personally, in my humble opinion, light, I believe, is actually strictly a wave phenomenon. That's my opinion. Like sound, because there's lots of evidence that it acts like a sound wave. It can be like canceled like a sound wave. It refracts like a sound wave. It travels through the medium at basically a constant speed. Because this is another thing. People say,
But how does it travel through space? There's no medium when it travels through space.
well, exactly. This is what the whole question about, you know, what is space made of?
Yeah.
See, it's a problem is if there's nothing in space, if it's a true void, then there's nothing for
And
a
nothing to
wave
travel
to wave in.
Yeah.
It's just a basic requirement. If you have something that's waving, there has to be something there. So, but once again, in my opinion, that actually proves that there must be something there, that there must be what they call an ether, right? There's got to be something, even in the vacuum of space, right? We know that in this room here, there's lots of air, right? So,
Right.
you know, light could be traveling through the air molecules, but we know that that's not true, because we can suck all the air out of a box and we can still shine the light through.
Yeah.
So
Yeah.
it's not anything that
It's not air.
we can readily detect or
Yeah.
see, whatever it is.
Yeah.
It's just, it's something that has been so hard to detect that we so far have no experiments that will definitively say, aha, in this vacuum box there's still something there.
Mhm.
But I contend that there is something there.
Okay.
We had to kind of discuss what that might have been. So, but I think it all comes down to electrons and positrons. So, last time we basically discussed that the whole world is being caused, everything we see being caused, like gravity, is being caused by electrons. They emit a negative charge field.
Mhm.
And then we have, you know, positively charged things. They emanate positive charge field. So everything has to do with charges. And so Simon, here, why don't you take that's a negative charge, and that's a positive charge. So what's the simplest way to put those together? I'll just go ahead and put them together. And see, that is the simplest way for a positive charge to mate with a negative charge, right? It's just glues right onto it, right?
Mhm.
It's not orbiting around or doing anything crazy. It's just sitting right on there, okay? So, and together, the charges cancel themselves out. So the positive cancels the negative, so that particle is neutrally charged. Now in my thinking, basically, I need to fill space with something that's hard to detect. So I'm going to fill space with these neutral, the most basic particles you can create out of a positive and a negative charge. That is the simplest thing it could possibly be. And so that's kind of what I'm thinking. So that light has something to travel through, right? So if light has something to travel through, then we can explain why is it that light travels, say, at a constant speed, and actually the way that's expressed is the actual way Einstein expressed it was that the speed of light does not depend upon the motion of the transmitter or the motion of the receiver, and the only way that can really happen is if light is traveling through some other medium which is setting its speed limit, just like the speed of sound, because the speed of sound is exactly that same way. Is that even if I'm walking forward and I talk, the speed of sound is not added onto the speed that I'm walking, or if I'm retreating.
Yeah.
It actually only goes at a fixed speed relative to the air that's in the room. The air sets the speed of sound as a constant, and so this ether, whatever that the light travels through, must set the speed of light. And curiously enough, that's what people initially thought how light worked. Everyone thought, oh, there must be an ether for hundreds of years, until they did one experiment, and then they decided, oh, it's not there. And so, even though there's just a ginormous amount of logic and evidence that would suggest that light is a wave, that there is a medium, all we have to do is just find the medium, and then, Simon, you can get the Nobel Prize if you can find the medium for light. And I'm just saying it's just a positron and electron stuck together. That's it.
So
Just have to convince University of Washington to go find that sucker, and then,
So where does
then my genius will be recognized. But until then.
Okay, while Simon's looking for it, can you have fun?
But, well, there's another thing. So, Simon, we're going to be looking at light in terms of what we can do with light. So I've got a few things here. So I've got two kinds of microscopes, you see? So, you can only see so closely how big things are. But have you ever tried using a microscope? Have you ever seen one of these things?
I've seen them in books.
You've seen
but
them
not
in books and
real
movies.
life.
Okay, well this is a real life microscope. Let's see if I can get it working. Okay. All right, so I've got a little light down there, and the way this works is that you put your eyeball up to this thing, and then you adjust this. And I've got a leaf here. So the leaf has a lot of fine structure in it. Stick it on top of the light bulb. And then you can kind of see the structures. I'm going to just take a look inside the microscope there and see how that works. And then you can try and adjust the focus, and you can see it get in and out of focus. So you're seeing that several, 60, 70 times as large as you would be able to do it with your eyeballs.
60 times larger.
So that's one kind of microscope. So that's we're actually transmitting light through the leaf, so you can see the structure of the leaf. So that's one kind of microscope. And then we have another kind of microscope here, where we're going to turn it. It has some little light. See, it's really cool. And then we're going to look. I'm going to look down through here. Okay, look down through there, and what do you see?
A whole bunch of things.
You see a whole bunch of dots, don't you?
Yeah.
Do you see any dots there? It looks like a perfectly blue thing, but when you look in the microscope,
I can see a few tiny dots there.
yeah, but then with the microscope, you can really see what's there. I mean, you can also look at things like the wood, or actually you could look at your fingers or something. It's like you could look at, you got some itchy spots in your skin. You could actually look at your skin with that.
Whoops.
Yeah, you could take a look and see what that looks like. You might have to move your hand around a little bit to focus a bit, but this is one of the cool things we can do with light. Is that the light we can basically
Here, let me see.
magnify it and make everything bigger. Now imagine you had a super powerful microscope, and it could see all the way down to like a single atom. Wouldn't that be cool? You could look, and some people have claimed that they've in fact been able to do that. They actually have some pictures, some microscopes that could actually see
A single atom?
a single atom. But now the question is, how are atoms built? Once again, let's go through the same exercise here, where I'm going to give you, but instead of that being a positive charge, we're going to call that a proton, a positively charged particle, and then the red one, hold that, hold the red one, pick up the red one, pick up the red one, right? There you go. Just go ahead, pick it up, and that's an electron. So those are the two basic components of any atom, right? Now, I was thinking about this one day, and I had like two rocks. And I was figuring, how would an atom form if like the one rock, like this red one, was a proton, and the other rock was the electron? What is the easiest possible way for them to combine to form the simplest atom, which is hydrogen? What do you think, Simon? You just like put them together again? Yeah, so is that not the simplest possible way for a proton and electron to bind together?
Yeah.
Yeah, it seems so simple, right?
Yeah.
And if I handed you another proton and another electron, can you try and stick those together in the simplest possible way, all four of them? Okay, that's one. And then the black ones don't go together, but the red ones do, right? So this would be like the second element, which is helium. And if I handed you a third set, where could you put those to make another atom? Yeah, you could stick that one there, and you could stick that one there. Yeah, see? So that would be like lithium, right? And if I handed you another one, where would this possibly go? Like that. See, so that would be the simplest possible way for what these are, 4 protons and 4 electrons. You just split atoms.
You split the atom. Can you reach it, Franklin? It's over there.
Okay, let's see here. We lost the bits. That's okay. All right, so that's a simple way to try and figure out, how you would build atoms. But surprisingly, that is not the way that mainstream physics sees it. Mainstream physics sees it as, what we do is we take all the positive protons and we jam them together in the middle.
But they don't want to stick together.
No, they don't want to stick to. They all want to fly apart, and then the electrons are all somehow
Oh, I see.
orbiting around
Oh.
this chunk of protons. This is how it's supposed to work
Oh.
in legitimate mainstream physics.
What keeps the protons together?
Yeah, what keeps the well? They say what keeps the protons together is the BS force. No, it's called the strong force,
Strong?
which is strong only when it's holding protons together. Otherwise, becomes negligible
Oh,
outside of that, and it's
Oh,
never
I see.
actually been directly measured.
Oh.
But it's the only way they figure it could be, right? Because they love what is called the planetary model
Yeah.
of the atom,
Yeah.
although that's kind of been put aside. I mean, because it's just very problematic to have the electrons flying around, because see, there's a problem that there's nothing to prevent the electron from just falling back into the proton and sticking together like that.
Mhm.
There's nothing. So,
Yeah.
but the problem is that they say that can't happen. So it has to keep
Oh.
everything
Oh.
somehow magically in orbit. Now, can you imagine that? We have all of our atoms are all combined together. It's very hard to imagine that if we have all the electrons flying around the outside of the atoms, why wouldn't they all just repel each other? Because they would, right? Their electrons are on the outside. They're repelling. As soon as they get close, they're going to repel each other, right? And due to the fact that the Coulomb force is so much stronger over distance, definitely. I mean, I would challenge anyone to come up with any kind of computer simulation that could possibly show that there's enough attractive force to pull them together, that the electrons will see the positive force of one atom and the negative of the other, and then it's even harder to imagine how that could remain stable, because you'd think in like a microsecond the electrons would go flying all over the place, they'd be deflected, they'd do all kinds of crazy things. But, that's what mainstream says, as opposed to what we just did, which was just the simple, let's just put the positive and negatives together, let's make our atoms solid, alternating positive and negative matrix. Right? So that's what I call the cubic atomic model, which is something that I came up with. So that's how I think,
I'm gonna go get my sweater. You continue on, I'll be
I
right
think
back.
that's how atoms work. Now, we're going to be looking at another thing about light. See, you notice all the nice colors we have on this disc?
Yeah.
See, and you can touch it. See, go ahead. See, what's happening is that the electricity is attracted to your hand wherever you put it. And you can see that it's generating just these specific kinds of colors, right? Blue, red, and green. Now, there is some question about why is it that like spectra, when you hit a bunch of gas with a bunch of electricity, you get these specific colors, but only these specific colors, kind of thing. Like if you had like the hydrogen and you hit it with specific energy, you would only get like 3 or 4 specific colors, just like this disc is showing. Now the question is, why don't we get like every color in the universe? And what that has to do, I think, is the fact that the entire world is in fact made out of Legos.
Oh,
Right? So we have Legos. You know about Legos, right, Simon?
Right. They're actually my hobby.
yeah.
Okay, so what's one property about Legos? So can I take this brick and just stick it anywhere on my plate here?
Yes.
No, I can't stick it there, right? Where
Oh,
can you make it so it sticks?
You put it on these little dots.
Yeah, you have to stick it on the dot, right? You can't stick it between the dots, it won't stick. You have to stick it right on the dot, right?
Right.
So the thing is that, like in this case, we're generating the light. So what's happening is like these little gray blocks, they're kind of like the electrons. See this big brown thing? That's like the main atom. So we have the electrons. And when you hit them with a lot of electricity like this, then that causes them to leap out of their spot and take another spot. So it might come up there. But after a while, they'll lose its energy and then it'll jump back down. Like there. See, that's there. That's called the ground state. And then it'll get hit by some more energy and it might jump up to here.
Okay, so more farther away is more energy.
Yeah, farther away is more energy. And whenever it falls back down, it actually gives up energy.
Yeah.
It's kind of like when you're bouncing a ball, you know, it hits the floor. Now the thing is that because it's in a Lego brick here, is that the distance that these electrons can be are fixed integer distances, right? They can't just be anywhere. Like, it can only go from here to there.
1, 2, 3, 4, 5, 6.
Yeah, 1, 2, 3, 4, 5, 6, 7, 8.
Yeah.
And that's exactly what happens around actual atoms, like in my plasma disk here. Is that the electrons are being kicked out, they're going up to a certain fixed level, and then they're coming back down. And so this is actually why the spectra is in these very, very fixed bands.
Because of 1, 2, 3, 4, 5, 6.
See, so this is evidence that the world is actually built out of Legos.
No, come on.
Because if it wasn't built out of Legos, then these electrons could take any position they want, and they could release any kind of energy when it hits the atom. But we don't do that. Yeah, exactly. That's what we call quantum. You know what quantum means? It means quantized. And it's ironic that for quantum physics, they haven't figured out that space is quantized. Comes in a fixed smallest amount. Just like this Lego plate here. Smallest amount, smallest distance. So if you were to look at any electron, you would be able to see that it cannot move just anywhere. It can either has to be here or it has to be there. It cannot spend any time in the middle. And that also means that another thing quantized, which is time, is quantized. That there is, you can't split time into infinitely small bits. That at some point there has to be some rule that says that basically everything has to move at the same time and can only move like one block, one stud away at each time, at each clock tick. That's it. That things can only happen in a quantized manner. So space is quantized. It's like all of space was just on a graph paper. You can only be in one spot at one time, and then you can only change where you are at according to the smallest amount of time. And then the final bit is that there's a smallest amount of matter that you can have. So those are actually the three actual dimensions of physical space: is the smallest amount of matter you can have, the smallest amount of time you can have, and the smallest amount of distance you can have, right? So some of my other dissident science friends have used that to basically derive all the other fundamental constants. He kind of worked his way backwards, but it's very interesting that using those three constants, you can come up with a bunch of other, which are currently known as constants, but are actually derived based on this idea that all this stuff is quantized. So we've got all that stuff quantized. But we can see that, you can see the different colors in our plasma globe here. And that's definitely, showing you the colors that are being emitted by the electricity in the globe here. And that's what's happening, is that we're seeing the electrons only take on these very specific colors because of the fact that we're all living in a Lego brick world. So, what do you think about that? You think we live in a Lego brick world?
Oh, come on.
Lego brick world, that's what we live in. All Lego bricks.
A whole bunch of them.
A whole bunch of Lego bricks. Now you see, I've gone on and, since I only have so many magnetic cubes, I made the Velcro cubes here so you can kind of see what bigger atoms would look like. Like this basically is oxygen. And the reason why it is oxygen is because we have something which is kind of shaped like this, and these things are helium, and helium is completely non-reactive, right? You can't get in. So what this is actually 3 helium atoms glued together, but then we have two half helium atoms, and because it's a half, that means it wants to join. It wants to make helium. So we can take another. This is like hydrogen, and it wants to go ahead and join like that. So it actually just docks on there like that, right? And then we could do another one here, and that just docks on like that. So this is why oxygen typically binds with only 2 elements, and together it makes water.
That's water,
right? See, now we have.
Two hydrogens.
See this? Did you believe this is water? Okay. And in chemistry class, we have our little models here. So Simon, I'm gonna let you play with these models here. So let's see. Can you go ahead and just, make me up some random molecule there? Just stick some things together. See what you come up with. Because really, actual atoms basically follow these rules. That, for example, for oxygen, the bond is about approximately 90 degrees kind of thing.
120 degrees.
Yeah, 120 degrees, that's right, 120 degrees, and it only really is allowed to make 2 of them, right? But if you have like a carbon atom, there can be 4 things attached to it.
So the black is carbon.
That would kind of be the case where, if I took off these 2 things here, then I could attach 2 more atoms, 2 more hydrogen atoms onto this to make, and this is basically carbon. This is why carbon takes 4 atoms basically in a cross pattern. See, so that's the amazing thing about, how.
Okay. Here we have CO3.
Okay, what have you made?
CO3. That's going to become another C.
He's got
2 CO3.
He's got 2 carbons and 3 hydrogens.
Oh, I see. Those are hydrogens.
Now the funny thing is that so what
CH3.
you made there, that could possibly be, an actual chemical compound that people need to use and love. Here, you need a few more balls. Maybe we'll throw you in a green one, right? There you go.
Green?
Just fill it out there. See what you come up with. Because basically what you're doing is what nature is doing. Oops.
There it goes.
Nature will go ahead and just, follow the ball and stick model and make something that might be useful or could be deadly or, could be totally random. Yeah, jam that hydrogen in there, okay. Is it not going in?
It doesn't want
Really?
to. It's not acting like a chemical at all.
It's not? Okay, let me see if I can get it in there for you. Yeah, that one's a toughie. Okay, I got that one in there, okay. You can attach the green one on there. Okay, you've got one. I think that's a nitrogen, maybe. But wait, there's more.
Perfect.
There you go, perfect. See, so you've created a molecule, right? 2 carbons and 6 hydrogens and 1 nitrogen, right? This could be some critical molecule required for the functioning of your body. We don't know, but this is a hydrocarbon because it's got carbons and hydrogen and some other odd atom glued onto it. But indeed, you could find something just like that. That's how atoms actually form as they were a stick. And like if you had a microscope that was powerful enough to see individual atoms, I think you would see something like this. And this is still a small atom.
Oh, that's a molecule.
No, this is a molecule, but say if that would be a singular carbon atom,
Yes.
right? So this would be singular hydrogen atom, is what that would be. But if you made like a really, really big, like I said, everything in the world is actually Lego bricks. That if you made like a really, really big atom, like this is like close to gold, I think, that it would end up looking like this. That everything would build out so that it's got this cross shape, right? And because it has a cross shape, where it's going to have its docking ports are going to be only on the edges, just on the vertices, right? Because that's where these available docking things happen, right? So for this model, you would think that you would have an atom up here, down here, to the far, and lo and behold, for large atoms, this is exactly the molecular shape that they form, right? See the similarities, right? They're both crosses, right? They're both, the reason why is because I think if you were to have a really, really cool microscope that could see like a gold atom, an individual gold atom, that you would see that it would look like this. So I'm just waiting for them to actually come up with a microscope that can actually look that well, because the reason why we are confused about the shape of an atom, not this, like I said, what mainstream science thinks is that all the protons are crammed into the nucleus with a whole shell of electrons flying around, is because we haven't had the technology to actually isolate the geometric shape of an individual atom. And so basically we've been going blind this for like 100 years. Like I told you, like people came up with the planetary model of the atom, and they just loved that idea. It's so natural. It's like planets flying around. Except we have like uranium, it's like 93 planets flying around the sun, trying in all random directions, not crashing into each other. That seems highly improbable. Versus this cubic atomic model where everything is solid, right? Solid, it's space filling. You can see where it attaches atoms to. I think it makes a lot more sense. But the only reason why we think that all the protons are jammed into there is because there's this one experiment performed by a guy. And what happened is that they basically, like, if you have a dark room and you fire bullets into that room, and then you kind of see what flies back, you could probably guess what's in there, right? Like if there was just like one steel plate sitting in the middle, you just randomly fire bullets, and you see when you fire to the right, you don't get anything. You fire to the left, but when you shoot it right in the middle, you get bullets flying back at you. So you can kind of guess, what's in there. Yeah. Now, effectively, that's how they determine that all of the protons are stuck in the middle of the atom, because that the only way they figured they could get something to reflect back is if all the positive charge in the atom are concentrated in one tiny speck.
Oh, I see.
But that kind of that doesn't really meet our intuition that, well, maybe it just hit something hard and it came back, right? That's our normal experience. If I throw a ball against the wall, it comes back, you know, not because it's being reflected by all these charges, it's because it's solid, and there's just the principle that, you know, two objects cannot occupy the same space at the same time, so it comes back. But they found that, you know, if you use a bunch of calculations, you can figure that they figure out, you know, that it has to be all concentrated in the middle, because only a certain percentage come back. So when they do this experiment, they find only some tiny percentage come back. In order to do that, they have to concentrate the protons in a certain way. But with my model, you can see that, well, if you shoot in a bullet and it goes through here, it's very thin, right? It's probably going to go straight through, right? It's not going to be stopped, right? It's not going to be stopped. But if you are like, if you hit it like edge on, like in its thickest part here, then it may actually put up enough resistance to shoot your bullet backwards, right? Or if you hit it straight on the top here, if you go through a thick part, you are going to reflect back. So, like I said, the guy whose name was Rutherford, he was the guy who came up with this whole idea that, you know, I could do my own calculations on this, and I did, and it's like, yeah, something of this shape, if you hit it randomly, you know, it will reflect back, you know,
Do you have something that
a
Simon,
certain
do
characteristic.
you have something that Simon can do with his own hands?
Yeah, you can look at the atom. You can see that is perhaps how atoms are made. So I have one, let's see here, I have one last thing, which is about light. Now, light is not just about the stuff that we can see. It's that one of the most useful things is actually like radio waves. See, radio waves are basically kind of the same thing as light. They travel at the same speed. So we have our plasma disk thingy here, and it's generating light. But now I have my Science Fair 101 electronic project kit here. So this is why I got into MIT, because I learned all my electronics on this thing. Although this is not the original one.
Could you move that out of the way?
Okay, so we see that. So this, what I've done here is I built a radio receiver here. This is a 3-transistor radio receiver. So see what happens when you touch the plasma there. Go ahead and play around and touch the plasma thing there. You can actually hear it. It's generating radio waves. You can calm it down. You can...
There you go. The middle.
Yeah, if you hit it in the middle. Yeah, give it a try.
No, it's not there.
There's another interesting thing that you can do is that you can actually light up LED lights. So it might be a little bit difficult to see, but if you put that next to the disc, you can see it actually light up a little bit. Put it right up there.
Here, look at that.
Whoa.
Here. Hey.
See, because it's transmitting these radio waves,
Yeah.
and it's exciting the phosphors in that lamp.
Yeah.
Now, I think that also works with this guy over here. Stick it over here. It's like
Yep. See
that
that?
also generates.
See that?
That also generates invisible electric light. You can see it light up. Isn't that amazing?
Yeah. Yeah.
Yeah.
That's amazing.
So what's making this go?
Now this
Is it-
thing
is it
has two different modes.
Self-contained?
It's self-contained.
Oh, okay.
So that's the voice activated mode, and then this is just random pattern mode. Although it will still react to you putting your fingers on it. Versus voice activated mode,
Oh.
you go ah ah
Oh.
ah.
Voice activated? Voice?
Yeah, scream at it.
Voice!
Oh, all right. All right. And what do you call this again?
This is a
Scatter
plasma disc.
plasma disc.
Yeah, and it's unique because it has the 3 different colors. I think that's because it has 3 different phosphors actually.
Simon learned about plasma in the first grade.
But that's the unique thing about plasma. And let's see, the last thing I have to show you is some ancient technology that's been sitting in front of you here. So what we have here is a tube radio. So probably none of your friends have ever seen one of these things.
Yeah, see,
But-
those are tubes.
What we have here is we have basically it's like light bulbs. Can you believe that we used to use light bulbs to make everything work? So I'm gonna turn it on here. And I gotta turn on the radio. And now we're listening through what you're hearing there is being amplified by these little tubes here.
Oh.
And you can see they're actually glowing. If you look in there, you can see the orange.
Oh, yeah.
See, it's literally a light bulb.
Oh, okay, so is that the speaker there?
Yeah, that's a speaker
That's
there.
that's the speaker there. It's not here.
No. And I'm just using that to send audio signal because this is basically an amplifier.
Yeah.
It is actually also a receiver, but a very poor one
Oh.
because it would be too quiet. You would not be able to hear it.
Mhm.
But if I put in a nice strong signal, then it can amplify. It can amplify it. Because this radio by itself can work. See, now it's picking up this guy, just like my other one. So it's like, so you can barely hear that, right? If I put it in my amplifier, then it's much louder. Okay, but that's just an example of, this is how all the electrons are flowing around, and this is how all of our modern stuff works, right?
So now we've gone to transistors.
Now we've gone to transistors, which are those things. You see these little metal cans there?
Oh,
Those are individual transistors.
Are you able to make different things out of that?
Yes, you can make like 100 different things.
Oh.
It's amazing.
Simon's going to do a little class next week at the library about circuits.
About circuits?
Yeah, they'll make 2 or 3 circuits during the little class thing
Yeah.
called silly circuits.
Silly circuits?
But it's for his age, 6 to 10.
Yeah, that'll be good because you learn how electricity flows around. You see, you've got all these wires in here, and the electricity is just flowing around all these things in order to create like what this case. This is the most complicated thing you can build with this kit, which is a 3-transistor radio. But there you go. So we have covered like what is light. Well, what is space? So space definitely has to be made out of something. So I think it's made out of like these neutral objects. And then we covered what light is, which I would say is a wave in that medium. So the medium has to exist. That's light. And then we covered, what are atoms, right? Atoms are just these conglomerations of like protons and electrons. Although I do have this question about what is antimatter. You know what antimatter is?
No.
No? Okay. Well, antimatter is actually the same as matter, but the opposite charge. So we talked about there being positrons and electrons. So actually the positron is the simplest bit of antimatter. it's positively charged. So what antimatter would be is something which is primarily made out of positive charges. Now there's a question of, well, what the heck is a proton? So a proton is not the same thing as a positron. What a proton is, I believe, is the simplest thing to make a one charge, a +1 positive charge thing would be 2 positive charges and 1 negative charge, right? This is the simplest way you could make a proton. You can see it's 3 times bigger than the electron. This is why it has more mass. Although, curiously enough, it has nearly 2,000 times as much mass. But what mass is just how difficult it is to push this through space. And even though it's only 3 times bigger, yeah, it's 2,000 times harder to push through space. It's kind of like if you're trying to, you know, if you had like a tennis ball and you squeezed it through a hole that just fit, it would take nothing to push it through. But if that hole were just a teeny bit smaller, then yeah, it would take a lot more energy to stuff that tennis ball through a slightly smaller hole. So in that way, you know, it's not linear. Even though it's 3 times bigger, it's 2,000 times harder to push through space, right? So, and I need to do some work to prove that. But now, so this would be regular proton. So what would be antimatter equivalent? Is that you would take 2 negatives and 1 positive. So this is antiprotons, all right? So you've got proton, you've got antiproton. See, and then you can create an anti-hydrogen atom. So this is a positron. Now you've got 1 positron and 1 antiproton, which makes antihydrogen. So that is actually the difference between matter and antimatter, right? Antimatter is just made out of these antiprotons, which just have more positives than negatives. That's it. And so there's this big mystery about, well, where is all the antimatter? You know, when the universe formed, the positive and negative charges should have all been evenly created. But yet we only see the regular matter protons. But the thing is that all of the antimatter is actually just bound up in the protons. Because there's still an even number of these things, right? You take anything that's neutrally charged, you know, this would be a regular hydrogen atom. It's still got 2 pieces of essentially antimatter, and then 2 pieces of negative regular matter. So it's like the charges are all there. Whereas all the antimatter, it's in the protons. Anytime you see a positive charge, that is essentially antimatter. It's just that for some reason, these got formed versus these. So that's still a question. Why is it we don't see a bunch of these things? We see a whole bunch, almost all of these things. But you know, that's still a question. But as far as where the antimatter went, you know, it was sucked into the protons. So, and I think that's what I have for you today. So there we go.
Okay, good.
There's plenty of Nobel Prize fodder to be had here as far as quantizing everything, how atoms are built, how light works, and all that stuff.
This is about the Nobel Prize. That's his way of saying there's lots of things you can discover.
That's right. There's lots of. We are still in the dark ages as far as physics goes.
Not everything's been discovered.
Not everything. There's still much to be discovered. So I encourage anyone watching this to, you know, consider those things, and yeah, go ahead like I have. I tried to figure these things out on my own. To go ahead and try and figure out these things on your own.
Okay.
So.
Okay. Good. Thank you. Thank you. Well, he'll do that